Hello and good evening, CTS110 Section 840 students for the Spring 2016 semester at Anne Arundel Community College. This is the CompTIA Nut Plus course, and this evening's video tutorial is going to be on Ipv4 subnetting, and then we're going to take a look at some symmetric key encryption in a neat little exercise where we get to access the Enigma encryption device, symmetric key encryption device. Basically, it's a web page that we're going to go visit, and we can put some codes in. All right, so let's first start with the sort of the low-hanging fruit, so to speak, which is going to be our Ipv4 subnetting. So as you can see here, we have a class C IP address, 192.162, and I have a feeling that that may be a typo. No, they are using 198.162. Okay, so we're going to stick with 198.162.10.0 and the Class C default mask. Well, we know that the Class C default mask is a /24 or a 255.255.255.0 dotted decimal subnet mask. Each subnet needs two host addresses, so it says build the subnetting scheme. The situation seems odd since it only has two host addresses. However, it would be used for subnets connecting, and these are called point-to-point connections that would be between routers, typically between routers. They can be between multi-layer switches as well, but typically you'll find these on point-to-point interfaces between routers. So the new subnet mask would be a /30, and so here we go. I think that's going to be, yeah, so we'll bring it down to right here where we can start to do some writing. Okay, so we're talking about the default mask is a /24, but we've got a requirement here. Each subnet needs two host addresses. Well, if I only need two host addresses, then my subnet mask would be 255.255.255.252, or in other words, a /30. Because if I only need two assignable host IPs, 2 to the 2 is equal to 4 minus 2 is 2. So that means we've got two host bits, so 0, 0, and then the other 6 bits in that last octet are going to all be network bits or subnet bits that have been borrowed. So 128 plus 64 is 192, plus 32 is 224, 240, 248, 252. And that's how we end up with that last value here in dotted decimal notation. And again, 32 bits overall in the entire subnet mask. If only 2 are host bits, that means that 30 of those bits have been used. So it says highlight the rightmost bit in the binary mask, which would be that bit right there with a value of 128, 64, 32, 16, 8, 4. So the block size is going to be 4. So the new subnet mask in dotted decimal, I actually wrote it up there, so it's going to be right here. New subnet mask in CIDR notation /30. So again, 255.255.255.252. New subnet mask creates, so how many subnets does that create? Well, 6 of those bits is going to be 64 subnets, right? So 6 subnet bits have been borrowed, so we get 2 to the 6 is equal to 64. And each of those 64 subnets will have 2 usable IPs because 2 to the 2 minus 2 is 2. So we'll have 2 possible hosts. Now, we're not going to do all 64 here, obviously. It wants the last 5 subnets only, right? Now, if it was the first 5, that would probably be pretty easy, but we want the last 5, which is just as easy because we have the most important value of all, the block size. Now, they give us the last value here, right? And actually, that would be, is that right? 252, 3, 4, 55, yeah. All right, so it's very, very simple from here where we subtract 4 to give us 248, 244, 4, 240, and then 236. So my broadcast IP would be 239, 243, 247. You can see they're going up by 4, and then 251. My usable IPs are going to be .237 and .238. So there are the two usable host IPs. And then we've got 241 and 242. We've got 245. That's going to be a 5 there. And 246. And then 249 and 250. Okay. And then 53 and 54. You can see that over here they go by 4, right, by the block size, and these increment by 4 as well. All right, so that is how you sort out the first part of worksheet number 9. And this was a little more difficult because we end up with some values that we haven't, we've talked about a little bit, but we've yet to kind of put into play. So this is all about the /30. All right, let's clear our screen here, and let's scroll down a little bit, and let's take a look at the symmetric key encryption. Now remember, the key with symmetric key encryption is that the same key is used, or the key that's used to encrypt the data is the same key that's used to decrypt the data. So we're going to be taking a look at the Enigma machine that was created by a German engineer at the end of World War I. And if you haven't seen the movie with, I think his name is Cumberbatch, the guy that plays Sherlock Holmes, there's a movie out with I want to say Benjamin Cumberbatch. I don't know if that's his first name or not. But anyway, it's a very, very good movie that's all about the Enigma machine and how he's playing Alan Turing in the movie, how he came up with the code to crack, or the machine to crack the Enigma code. And it's absolutely a brilliant movie. And it's as exciting as it is, and as good of a movie as it is, it's just as tragic a story as well on an individual basis for Alan Turing. But a great movie. I would highly recommend that if you don't get a chance that you go see it. So I've already got this web page up here. So how now brown cow. There we go. So here is the website, right? And that's all you need to do to get to it. So we're going to input. I'm going to say how now. How now brown cow. And then this is the output that we get. So let's copy that. Let's make sure we're following directions here. So the Enigma simulator. So encode a short sentence. How now brown cow. We see the output, right? No need to type uppercase letters. It's automatically going to do it. So copy the encrypted message of the clipboard. Okay, next we're going to hit the reset button in the initial state. Okay, so the next thing that we're going to do is we're going to hit the reset button, and we're going to put in the input, which is our message, right? Or I should say the encrypted text. And here is the output. And again, we're using A, and O on the dials here. So these are sort of the keys, A, and O. All right. So it shows that the same message that's in the inbox, or I'm sorry, the same message that we encrypted is the same message that we decrypt. So now let's go ahead and take a look here. They want us to start by resetting the machine. So let's see what happens if I take this message and I copy that and I put that in. The rotor positions are supposed to be CTS, right? Like CTS110, but right now they're AAO. So what happens if I reset this, and actually it's AAA, if I reset that and I say that that is the input, what do we get as the output? You can see it's just a bunch of garble here, right? That doesn't go decode to anything or decrypt to anything. So let's set these correctly here. So we want to set this to C, and then T, and then S. So there we go. So the rotors are set. CTS Now let me paste in our encrypted code, and what do we get? Cryptology is the study of codes. So there you go. So if you wanted to, you could create a message, and let's do it again. So if we were to set this to A, B, C, and type in all work and no play makes Jack a dull boy. And I'll even throw a period in there. Oh, it won't let me put the period. All right. So all work and no play makes Jack a dull boy, and that was with A, B, and it flipped it to J actually up there on us. But this is what we get for the encrypted text. And again, if I were to reset this and say AA J and provide the encrypted message, and actually I think it was AJ, let's reset here again. I think it was A, and now I can't remember. All right, well, you get the idea. So anyway, this is a cool little website here where you could put it in, and again, it's symmetric key encryption because the same key that we're using to encrypt the data is going to be the same key we use to decrypt the data. All right. So again, it would be that cryptology is the study of codes. All right, well, this is going to wrap up exercise, or I should say worksheet number 9. Enjoy the rest of your weekend, guys, and I will see you all on Tuesday evening. Have a good one.